Good afternoon, students. Today I will present the first lecture on the course dedicated to the basics of quantum dot physics in the frame of the course of Photonics. During the first lecture, I will mention a few problems from the elementary quantum mechanics. What is the main object of the quantum mechanics? It is a particle. And what are the main questions? First one, what is the energy of the particle? And second one is what is the character of the motion of the particle? If we want to describe a particle energy, firstly we will put it in some very simple model space. Potential well is a commonly used one. So a equation that describes the particle energy in the potential well is the time-independent Schrödinger equation that you see here. In the Schrödinger equation, this function is the potential energy of the function as the function of the position of the particle inside the well. C function is the stationary time-independent wave function. M is the mass of the particle, and E is the real number of the energy of the particle. There are two kinds of potential wells, infinite and finite ones. What does it mean in potential well? Especially, potential well is such a region that surrounds the local minimum of the potential energy. It means that inside of this well the potential energy is equal to zero, but starting from the edges of the well or its walls, the potential energy is almost infinite. When the particle gets somehow inside of this well, it is very hard for it to get out of it. The physical representation of the infinite potential well is a box with the very, very high walls. For example, if we have some box in our home and we throw a ball inside of this box, even with a very, very high energy, there is a very little possibility for this ball to jump out of this box, because the walls of the box is very high. So this situation also happens in quantum physics. What else about infinite potential well? So because the walls of this well is almost infinite in their height, total number of states, energetic states of the particle inside of this well is also infinite. The energy of the particle inside of the potential well is fully quantized, and the energy of the particle is connected with the square of the principal quantum number. As you see, the energy of the particle has definite separate levels. This means it is quantized. The wave functions of each energy level vanish at the walls of the potential well, as you can see here. The probability of finding a particle inside of the well is equal to unity. So it means that we are definitely sure that the particle inside of the well, not outside. The probability of finding a particle can be mathematically represented as the square of the model of the wave function. So the probability is equal to unity, and the square of the model of the wave function is also equal to unity. What else about infinite potential well? The Schrödinger equation that I present you in the first slide have different types of solutions, even and odd type. This is connected with the even and odd value of the principal quantum number. But if we bear in mind the probability of finding a particle inside of the well is equal to unity, so we can just take these solutions of Schrödinger equation, take their model, and then take the square of the model, and all of this is equal to unity. Based on these equations, we can get the energy level of the particle that can be expressed like this. We also hear that here we see that they are also quantized. The spacing between neighboring levels is also quantized and is dependent on the principal quantum number as well. But we still remember that potential, well, the particle is still the potential well. It means that this energy of the particle is fully kinetic energy, and we can rewrite this expression in the kinetic type, which connects the value of the energy with the mass and the momentum of the particle. If you look here on the energy level of the particle inside of the well, you can notice that the minimum energy level is when n is equal to unity. But what about a situation when n is equal to 0? Can it be realized in our world? Let's think. We know that the energy is connected with the principal quantum number. If the principal quantum number is equal to 0, it means that the energy of the particle is also equal to 0. But also we know that this energy is kinetic and it is connected with the mass of the particle. So if the energy of the particle is equal to 0, so it means that the mass of the particle is also equal to 0, and this means that the particle doesn't exist inside of the well. That's why the minimum energetic level is connected with the principal quantum number equal to unity. And this principle is called the particle's zero-point energy. What's the point? We call this principle zero-point energy, but zero point of the particle connected with the principal quantum number equal to unity, not to 0. Here, I think we should remember Heisenberg's uncertainty relation. Oh, sorry, not this Heisenberg. And we remember that our particle is still in potential well, which has definite width. So delta x here is equal to a, which is the width of the well. And the uncertainty over the momentum of the particle can be written like this one. And the uncertainty of the energy, of the kinetic energy of the particle based on the uncertainty of the momentum can be written like this one. Remembering the equation from the previous slide, which connects the interspacing between two levels, we can compare the expression number 1 and expression number 2 and obtain the accuracy of the first energy level of the particle, which will be this one. So the main points from the previous that I have said is that the following. The energy of the particle is quantized. The lowest possible energy of the particle is not 0. This means that the particle always has some kinetic energy, even at 0 Kelvin point temperature. The symmetry of the potential well determines the symmetry of the particle density. And the particle density is the probability of finding the particle in a specific position for a given energy level, which is represented by the square of the module of the wave function, this one. But what if a box has the finite whirls, like in the real world? It means that we will have a particle in an ordinary box. And there will be such situation that, for example, if we have some box at home and we will throw a ball inside of this box with a very, very high energy, very hard, then in this situation the ball will have the opportunity to jump out of this box. If you throw a ball in the box with a very little energy, like so the ball in this case will stay in the box because he doesn't have enough energy to jump out of it. In the quantum mechanics, the case is the same. The wave functions of the wave functions of each energy level of the particle, which is situated in the finite potential well, do not vanish at the edges of the wall. But outside the edges of the wall of the potential well, wave functions exponentially fall in every case, in every energy level. The probability of finding a particle outside the well is non-zero anymore. And with growing principal quantum number, this probability increases. Here is what I said. The more the energy of the particle, the more the possibility to find it outside of the box, like the ball, the throw. The states with the energy that are higher than this level, so they are higher than the height of the box, correspond to the infinite motion and form a continuum. And at least one state always exists within the well. So these are the main difference between infinite potential well and finite potential well. So as I have just said, the number of states inside the well should be more than one. And because the walls of the potential well are finite and the potential well has definite height, the number of states can be determined somehow by this equation, where u0 is the height of the well. Here you can see also the mass of the particle. Also, the difference between the finite and infinite cases is that absolute position of the energy levels in the finite case is lower than for the infinite potential well case. Let's look at some definite example. For example, we have an electron in the potential well. The width of the potential well is 1 nanometer. Then, using previous equations, we can calculate that the energy of the first level is this one. The energy of the second level is this one. The interspacing between these two levels is equal to this energy. So, for example, our electron force is making a transfer from the second level to the first level. During this transfer, some energy will appear, and this energy will be equal to the interspacing between these two levels, because the energy is quantized. This energy is corresponding to the wavelength of about 4 microns. This means that if we have some material with which contains such potential well with the electron, and the electron is making such transfer, this material will emit radiation in the mid-infrared region. Maybe it will be a laser or something like that. Let's go further. If we have a particle not in one-dimensional potential well, but in a spherical potential well, this is the three-dimensional case, and we will have to solve the three-dimensional equations. It will not be the Schrödinger equation, it will be such Hamiltonian, and the R will, the radius of the potential well will be connected with the 3 arguments. In this case, we should go really from the linear arguments to the spherical or radial arguments, which contain the radius of the spherical potential well and 2 angles, because their problem is three-dimensional. If we transfer our Hamiltonian from the linear arguments to the radial arguments, we will obtain these 2 equations, that are really big and very hard to solve. So let's try to simplify them. If we simplify the wave function from that Hamiltonian, we can separate it into three functions of three different arguments. And we will get this equation, where this is the spherical Bessel functions, and this satisfies the equation that looks like really very familiar, and we definitely know that it's not any more three-dimensional equation. This is a one-dimensional equation, and we can definitely solve it. For that is, if you were very, very observant, you noticed that the wave function has very familiar subscripts n, l, and m, and you will be very, very right if you think that this looks like three quantum numbers, and you will be sure. The state of the system is characterized by three quantum numbers: the principal quantum number n, the orbital number l, and the magnetic number m. The 3D model of the orbitals with different quantum numbers you can see here. The orbital quantum number determines the value of the angular momentum, and the magnetic quantum number determines the number of L components that are parallel to the z-axis. What does it mean? If we have orbital number equal to 0, in this case the magnetic number also will be equal to 0, and we will have s states or s orbitals, and the number of such orbitals is only one. We have only one s orbital, as you remember. If the orbital number is equal to 1, to unity, then we will form p states or p orbitals, and there will be three magnetic numbers that corresponded to these states. So it means that we will have three orbitals. Here you can see that I wrote the number of degenerate orbitals. What does it mean, degenerate? For example, if we take two functions of argument x, and at one point and at one value of this argument x, these two functions intersect. So at this one specifically definite point of argument, these two functions have the same value. Then these functions will be called degenerate at this point. So what do I mean here? If we have three degenerate orbitals, it means that electrons on these orbitals will have the same value on this level. So if we have orbital number equal to 2, we will have d states or d orbitals, and there will be 5 degenerate orbitals. On the orbital level equal to 3, we have 7 different but degenerate f orbitals or f levels. The interesting point here is that the origin of the s, p, d, and f notations of the orbitals was formed during the early stages of atomic spectroscopy, and they were related to the obsolete sharp, principal, diffuse, and fundamental namings. So we don't use them anymore. In the previous slides, we definitely transform our three-dimensional problem to the one-dimensional problem, and now we are dealing with a rectangular spherical potential well with the infinite barrier. The energy values inside of this well can be written like this one, and these are the roots of the spherical Bessel functions. I really don't remember how this letter is called. I think that it is some like he, and he are the roots of the spherical Bessel functions. N is the number of the roots, and L is the order of the function. In this case, the principal quantum number n determines the number of the nodes of the wave function inside of the well. When n is equal to unity, it corresponds to having no nodes. When n is equal to 2, it means that there is one single node. And when n is equal to 3, it gives rise to two nodes. L is equal to the number of nodes in the wave function as the polar angle varies between 0 and p. That's why when we have L equal to 0, the roots of the spherical Bessel functions are multiplies of p. So 1p, 2p, and 3p corresponding to the values of the principal quantum number. According to these roots of the spherical Bessel functions, you can go here and see that here is the exemplary energy level of the different orbitals of the electron in the atom. But it's not really exact, really. And here is the case of the spherical finite potential well. And in this case, the minimum potential energy will correspond to this case. If we have P in this expression, we'll have the minimum of the potential energy in the finite spherical well corresponding to this equation. And this value is really very high. So it means that if we have a particle with a potential energy that is equal to this minimum, then we will have only a single energy state that can exist within the well. But if a particle has a potential energy lower than this minimum, it means that no one state can exist in the well at all. And this is the main difference between the three-dimensional case and the one-dimensional case. So in one-dimensional case, the minimum of the potential energy is 0. But in the three-dimensional case, the minimum of the potential energy is this one. So this is the main difference, please remember it. If we go further, we will describe the electron in the Coulomb potential well. What is a Coulomb potential well? Really, it's a kind of the spherical potential well, and it is one of the most important cases of the centrally symmetric potential wells. If you remember from your school classes, the potential of the electron can be written like this one. I remind you that this is the case when the electron interacts with some particle which has such huge mass that the charge of the electron does not disturb it. So for this case, and here you can see the dependence of this potential. But still, we remember that Coulomb potential well is a spherical one, so we should go from the linear arguments to the radial ones, and we can rewrite this equation like this one and use some dimensionless length and energy, epsilon and rho. The values that are written in the bottom of these equations can be called atomic length and atomic energy units. What are they? These are units of length and energy that were calculated using this Coulomb potential and the expressions of the energy that were presented in the previous slides, namely for the case of the electron. so the electron charge and the electron mass. And we got these values. But these values are like mathematically modeling values, and they don't have some physical representation. What should we do with them? Their energy level, according to the Bessel function solutions, obey such series. So we see that the energy level is connected with this expression, where the expression in the bottom is the principal quantum number, which can have only positive integer values beginning with unity. And nr is the radial quantum number that determines the quantity of nodes of corresponding wave function. This means that if we have the energy level of electron, the bottom energy level will have the energy that we have calculated in the previous slide, this one. And other energy levels will situate it on the energy level scheme according to this dependence. The total degeneracy of the state of which state will be like this one. But what if we take not some undefined electron in undefined atom? What if we take such definite atom as, for example, atom of hydrogen? We know that there is only one electron there, and it will be easier for us to calculate all the energy levels of the electron. So if we try to do this, what do we have? We can calculate some atomic radius of the hydrogen atom, but instead of the mass of the electron, we should use the reduced mass. Why? Because in the Coulomb potential, electron is interacting with some particle with a huge mass. But here we know that in hydrogen atom we have electron that is interacting with the proton, and we know the masses of both of them. So we just use the reduced mass mu that can be calculated like this one. Here is the mass of the proton and the mass of the electron. And when we use such reduced mass, we will obtain atomic length unity that can be called Bohr radius. What is Bohr radius? We know that if we take the energy level with the quantum numbers, such as principal quantum number equal to 1, to unity, and the orbital quantum number equal to 0, we will have the s orbital that are the closest to the which is the closest to the center of the atom, and the s orbital is the orbital where is the probability of finding the electron is the biggest. So the Bohr radius in this case will be the radius of the s orbital, and also the radius of the space where we can definitely find the electron of the hydrogen atom. If we take this Bohr radius and try to calculate their Rydberg their energy, which corresponds to this sphere with this radius, we will obtain Rydberg energy. What is it? It's the energy of ionization of hydrogen atom. What is ionization? Rydberg energy is the energy that we need to, if we want to tear off the electron from the atom of hydrogen and to have only nuclear of the atom. So the ground state energy of the hydrogen atom will be not 13.6 with minus, but 13.605 with minus. This will be the energy of the ground state of the hydrogen atom. So, during the first lecture, I've tried to explain to you how complicated quantum mechanical equations can help and can explain the simple chemical solutions. Thank you for your attention, and we will meet next on lecture 2. Bye.